Welcome back to ROBT402, Robotic Mechatronic System Design course, Lecture 12, S7, Graph Programming in TIA. Today's topics are as follow: sequential control, properties of sequential control, elements of a sequential control, programming example, and programming exercise. What is a sequential control? A control system in which the individual steps are processed in a predetermined order. Progression from one sequence step to the next being dependent on defined conditions being satisfied. So here you could see a flow chart and sequences of the steps, and these are the transition conditions. We could go from one step to another only if the transition condition is valid. The control procedures executed in succession are divided into sequence steps. So these are steps, and you could see that all of these steps will make a full procedure. Step contains one or more actions such as switch motor on or off. Only the actions of an active step are carried out, or the process one. So at the time, only one step is active. We cannot have, let's say, this step and this step to be active at the same time. Okay, at the time we only have one active step. Progression to the next step is carried out by means of transitions. These are transitions, step enabling conditions. So these are some conditions that should be valid so that we could progress or proceed from one step to the next one. The transition can be process dependent, for example, as a result of signals from the control machine or plant, or time dependent, for example, following expiry of a delay time, or combination of the time dependent and process dependent. Okay, so process dependent, for example, if a limit sensor or switch is on, then we could proceed from this step to the next one, or after 1 second, after 5 seconds, this step should be deactivated, and we should proceed to the next step and activate the next one. Okay, so that's the time dependent. So here you could see that we are basically we have sequences, okay, from step to the A step and to the B step, and we have transition from one step to the other and vice versa. So this is the vice versa, that we will return to the first step. Okay, we call this step here stop, or we could change it to whatever name we wish. Here we name this step A and this step B, and this is the transition 1, transition 2, and transition 3, and we have a closed loop. Okay, so in continuation of definition of sequential control, we have a sequential control is started at an initialization step. Several can be present in a sequential control. So here you could see in the TIA portal, if you have a sequential control, or we call it graph programming. As we go forward in the following slides, you will learn more about graph programming, which is the same as sequential control. One of the steps should be the initialization step, or the initial step, or we could have multiple initial steps based on the condition. These are followed by alternate transitions and steps in a linear sequencer. So you see that we have again transition conditions, and we have a linear sequencer. Okay, everything is linear. We move from one step to the next step. Branches are possible in addition to the linear progression. So we could have branches, we could have some branches, and we will explain different type of branches. The first type of branches are OR branch. With alternative branching, okay, this is the name for the OR branch. With alternative branching, only one of the following partial sequence is processed. So, okay, when it comes to the example, it will be more clear. But for now, based on the transition condition, we should either process one branch or the next alternative branch. However, with this simultaneous branching, as it is clear from the name, or AND branching, all following partial sequences are processed. So at the same time, simultaneously, we are processing two branches at the same time. A sequential control can contain several independent sequencer. Okay. So here we have one example, one sequencer, components and properties of a sequential control. And here is one function block graph. So we need to create a function blocks, and inside the function blocks we will have the graph programmings or sequencer. In the graph we have permanent pre-instruction and permanent post-instruction. In most cases during our lecture, these two gray area, which are pre-instructions and post-instructions, are empty. Okay, we don't put any programming here. Okay, so here is the main part of the graph programming or the sequencer, and you could see here that we have steps and transitions. Okay, so this one could be the alternative, or it could be a simultaneous branches, and I will explain which one is that later in the coming slides. Since we have a function block for this program, this function block is associated with the data block. Okay, and that data block will be saved inside the memory of the computer. Properties of sequential control, options for determining the way the parameters of the graph FC is shown, or the function control is shown, minimum, standard, or maximum. And we should go to the option PLC programming, graph, and interface. So here you see that here we have this maximum interface parameters. Okay, so you should choose these settings. To have a complete set of inputs and outputs in your function block. Program for a sequential control quantity framework. The instance data block of a graph function block contains the structured data of the sequential control. It can accommodate up to 250 steps and transmissions. One step and one transmission are only handled as a pair here. Up to 249 simultaneous branches are possible, and up to 125 alternative branches are possible. Operating modes. Automatic mode. A switch is made from one sequence step to the next when the transition between them is fulfilled. Okay, so all of these information now could be a little bit overwhelming for you, but when it comes to the example and you start to do the example and to basically do the practical session, then you will see that all of these concepts will fall into place and you will learn what do they mean exactly. Semi-automatic mode or jogging, a switch is only made to the next step if the transition is fulfilled and the manual transmission signal is present. Automatic or semi-automatic mode, step enabling, a switch is made to the next step if either the transition is fulfilled or a manual transition is present. And manual mode, the steps are selected by means of the step number and activated and deactivated individually. The operating modes are set in the parameters of the graph function block. So here is the graph function block. How could you create that graph function block? You will see in the example. Okay, so let's back now to the again concept of sequential control. What is a sequence step? Here we have step 1 and step 2. Sequence step contains the actions which can be programmed as tables. Is identified by a number and or name. The actions of a step are only executed if the step is activated. An interlock condition for each sequence step can be configured with which the actions in the steps are controlled. Okay, so these interlock conditions are extra conditions inside the step. Okay, in most cases we don't use these interlock conditions, at least for the purpose of this course. Transition, these are the transition, contains the condition required for the progression of the sequencer, okay, to move from one step to the next one. Ladder or FBD, which is function block diagram, can be used as the programming languages for the step enabling condition. So inside the transitions, we mostly use ladder logic, However, inside the steps, we have tables. We have tables, which in those tables, we say what actions should be done, or those actions are instructions and commands. A transition is identified by a number or name. So here is the name T1 or T2. More elements of a sequential control: sequence end and jump. Sequence end. This is the sequence end. You see this dot, a big dot, terminates a sequencer. So when it comes to this dot, everything is finished. It's terminated. Always follows a transition. So we need a transition. After the transition, the sequencer will stop. The program will be finished. If the transition is fulfilled, processing of this sequencer is terminated. Or we could have jump, which is also very common. Transfer from a transition to any step in a sequencer which is present in the same sequential control. So in some cases, of course, you could close the loop, for example. However, when the sequential chart becomes big, it's easier to have a jump. So say jump to the SM, okay, and then it will jump to the step M. Always positioned after the transition. So we need the transition. After the transition, we have jump. If this is fulfilled, the jump is made to the specified step. So we are jumping to steps, not transitions, which is then activated. It is permissible to jump to a destination from more than one position. So we could jump to a couple of more steps. Well, it depends on the program and the branching, we need to see the feasibility and the properness of jumping to more than one step. Okay, so processing of a sequencer. The processing of a sequential control is started by calling the graph function block. So once the graph function block is called, then we will jump inside the function block. So here we are inside the function block. The first step process when starting a sequential control is the initial step. Okay, so we need to choose the initial step, and we could right click on one step and select it as an initial step. So for example, here step 5 is selected as the initial step. Okay, so you see that these double border lines, and they show these double border lines, they show that this step 5 is the initial step. Okay, the first process when starting a sequential control is the initial step, and you identify this step when configuring. So we selected, for example, here step 5 as the initial step. Processing of a sequencer. The actions in a sequencer step are carried out if the step is active. The following transition is then also valid and is processed. If a valid transition is fulfilled, the previous step is deactivated and the step following the transition is activated. If the last transition is followed by a sequencer end, processing of a sequencer is terminated. To restart the sequential control, apply a rising signal edge to the input parameter init skew of the graph function block. So this is the if we basically send the rising signal edge to this input, what does that mean? It means that we have a false to true signal. Okay, so if the logic here goes true from false, then the function block that contains the sequencer will be called. So here we are inside the function block. Simultaneous branching and branching. So you see that we have this double line here. These are main characteristics of simultaneous branching. Shows that we are in a simultaneous branching or AND branching, and we only have one transition here. Okay, so these are the main characteristics of a simultaneous branching. All branching are processed in parallel. So once this transition is fulfilled and we could progress from this step to the next, then both of these branches will be executed at the same time. Each simultaneous branch commences with step. The simultaneous branches are combined following the respective last step. The subsequent transition is valid, i.e., it will be processed if the last steps of all combined simultaneous branches are active. Okay, so for example, this branch could be finished earlier than this one. So we will stay here at this step until this branch also will be finished. We need to have both of these branches finished, then we could proceed to the next step. Simultaneous branch finished by a sequence end has no influence on the rest of the sequencer. Okay, so you see that this is an AND condition. Why? Because if this transition condition is valid, we need to execute this branch and this branch and at the same time. Alternating branching or branch. Only one of the branches is processed. So you see that we don't see that double line here. Plus, we don't have transition right before the branch, but we have transitions before steps inside each branch. So each branch has a transition. Each alternative branch commences with the transition, which is opposite of the AND branching. In the AND branching, we need to have steps, not transition, at the beginning of each branch. If two or more transitions are fulfilled simultaneously, the step becomes active, which follows the transition, which is on the furthest left. So okay, so when it comes to transition, if this transition is false, for example, and this one is true, then this branch will be executed. But what if both of these transitions are true? Then the program only will execute the one on the furthest left, and this is the one. Okay, so the first branch will be executed and the next one will be ignored. The combination of alternative branches corresponds to an or condition. Why or condition? Because either this one or this one will be executed. An alternative branch can be finished by a sequence end or a jump. A data structure is created in the static local data for each configured step, for each configured transition, and for the sequential control. Okay, so now let's see what are the graph specific tags for the steps and for the transition. These are graph specific tags that will be created automatically by the program. Once you create the step or the transition, those tags will be included. So step activation time. The step activation time started when activating step and delivers two values. Step name T, total duration, which has passed since activation of step, and step name U, uninterrupted duration, or the duration from the start of step activation minus the duration for a fault triggered by the supervision function. This supervision function is an advanced function or feature, so we don't use it, and our steps won't be interrupted by this fault trigger. So what does that mean? Uninterrupted duration of the step. So once the step is active, the time will start to clock and will accumulate inside this step name.u. Okay. However, this step name.t is the total duration which has passed since activation of the step. So the step could be paused for any reason, and the total time could be paused for any reason, and that will be inside the step name.u. However, the whole duration from the first time the step is activated will be inside this step name.t. Step status, we have step name.s1, signal state 1 for one processing cycle if the step is activated. Step name.x, signal state 1 means that the step is activated, and the step name.s0, signal state 1 for one processing cycle if the step is deactivated. And we have transition status, transition name.tv, signal state 1 means the transition is valid. Transition name.tt, signal state 1 means the transition is fulfilled. And transition name.ts, signal state 1 means the transition is switched. Again, lots of info, and you don't know for now how could you use this information. In the example, you will see some part of these tags and how you could use them. Pre-instructions and post instructions in the permanent instruction. Permanent instructions are program components which are processed in every cycle independent of the status of the sequential control. We have pre-instructions processed prior to the sequential control and the post-instruction process after the sequential control. Permanent instructions can be programmed in ladder logic or FPD. Any number of permanent instructions can be used. double click on the permanent instruction in the graph navigation. So here is the permanent pre-instruction and permanent post-instruction. Click on the permanent pre-instruction or permanent post-instruction symbol in the toolbar of the working window. So you see that once you click on the permanent pre-instruction, then you have networks and you have a rank. Okay, so you could start programming with ladder logic. And finally, programming the graph function block example. Okay, so you might have some difficulties congesting all the concepts in the previous slides, but hopefully in the example you will get at least the general concept. In the project tree, okay, now we are in the TI portal. Okay, so you need to create a new project. In the project tree, open the program blocks folder under the PLC station and double click on add a new block. So we want to create a new function block. In the add new block window, select the function block as block type and graph as language. So here you need to select a function block, okay, and then you need to select the language as a graph. Select a meaningful name for the block, for example sorting sequence, okay, for the sorting station or whatever name you wish here. Click OK and go to the next step. Okay, in this example you are going to write the code for controlling the sorting station of the MPS 500. The sequence of the operation is provided below. Again, you could test your program in PLC. Initialization. Turn off the conveyor. Okay, in the initialization, turn off the conveyor. Which conveyor you mean? That's the small conveyor on the sorting station. Release the shunt 1 and shunt 2. Okay, put them in the straight position. So shunt 1 and shunt 2 are those basically guides which lead the parts into the slide 1 and slide 2. Activate the stopper. What is that stopper? That stopper is a single acting pneumatic actuator. Wait for 2 seconds and switch to the next step. Step 1. Buffer. Wait for the workpiece to arrive. Okay, this is the sensor. This is the optoelectric sensor. Then switch to the next step. Step 2. Examine. Once the workpiece is available, turn the conveyor on. Check the material. Okay, how could we check the material? By the this is the proximity sensor and the color. So proximity sensor could only check metallic parts. Okay, could sense metallic parts. So combination of metallic and the color, we could sort the parts. If the part is silver, is metallic. If the part is red or black, also could be identified by the optoelectric sensor, which is another optoelectric sensor. Wait for 2 seconds and go to the next step. Step 3, retract the stopper. Okay, so that stopper kept the part in place for identification. Now we have identified the part, we could release the part. Then, based on the material and the color, put the shunts into the straight or branch positions. Go to the next step as the workpiece enters into the slide. So, what is this sensor? I0.3. This is retroreflective optoelectric sensor, and that optoelectric sensor will sense if the part has already slided into the slides. Okay, so we need to continue the process, and that will be done in the step 4. Wait for 2 seconds and then go to the step 1. So why? Because we need to wait for the next part to be arrived, and then we need to repeat all of these steps to sort that part. Once you add the function block, the content of the block will be similar to the figure below. So you need to double click on that function block, and then inside that function block you will see this picture. An empty step and the transition will be shown. The step is automatically called S1 step 1. However, you could change it later. So you could change the name step 1 to whatever you wish, but this is 1. You cannot change it. Okay, so this, what is that? This bluish, no, green. Yeah, this green S1. You cannot change this name or T1, but you could change step 1 or trans 1 name. Declare the following tags as you are going to use them in the project. So go to the PSC tag and declare these tags. So from the addresses in the description of the example, you could better understand each one here. That, for example, this Q0.1 is the shunt 1 motor or the shunt 2 motor. We have a stopper motor. We have a conveyor motor. And we have some sensors. Slide is full. Slide is full is the retroreflective photoelectric sensor. We have this I0.1, which is metallic, non-metallic sensor, which is basically a proximity sensor. Okay, we have not black or black sensor, which is optoelectric sensor, and we have a part available or availability sensor, which is another optoelectric sensor. Okay, we have these comments, okay, which will help you understand what are these tags, and we could use them inside our program. Double click on the step 1 to see its detail. Okay, if you double click on that, then you could see the actions. Change the name of the step into initialize and provide some comments. So we have changed it here to initialize. Okay, we have interlock condition or supervision. Okay, ignore these ones. These are more advanced programming features. Under the actions, you have table. Okay, so you can see the table. In the action section, reset all the mentioned variable. Okay, what do we mean by reset? We are setting them to 0. Why? Because this is an initialization step. So this is are set to 0 for the conveyor. So we want to turn off the conveyor motor. We want to turn off the shunt 1, shunt 2, and the stepper. We want to turn off all motors in the initialization step. So now you could understand what we mean by having a table instruction under the actions. As the transition condition, set 2 seconds of the activation of this step. So in the transition, double click on that. You will see this rung here. Okay, inside the rung, you want to include this 2 second. Okay, how could you where you could find this here? Okay, CMP more than T, greater than step activation time. Okay, so under the comparator operation. And this is the initialization.t, those specific transition flags that comes with the program, comes with the step, comes with the transition. Okay, these are the internal tags. So once the initialize.t is more than 2 seconds, then we could transmit to the next step. Place a greater than step activation time block and put it into the transition. Change the time to 2 seconds. Okay, the T sharp to S. Add this step and transition. Call this step as buffer. So the next one. Okay, how could you add? I will show you later how you could add it here, but since we are inside one step here, you have a different toolbox. Okay, once you are outside of the steps, you will see adding steps. I will show you in the coming slides. Hopefully you will have a chance. Okay, so add a step and transition. Call the step as buffer, change the name, and for the transition use a contact associated with the availability of the part as shown below. Okay, so inside the action of that step, we don't want to add anything, so just leave it empty. However, inside the transition, we are using the part availability sensor. Okay, once this one is true, then we will transit to the next step, and that's the buffer step. The next one, if you add the next step, this is examination. Add the step and transition. Call this step as examination. And for the transition, use a contact associated with the time spent in this step. Okay, in the action part, turn on the conveyor motor. So set to 1 conveyor motor, and this is the address Q 0.0. For how long are we willing to keep this conveyor running? For 2 seconds. Okay, so after 2 seconds, we will move forward. However, since we set that conveyor, that will stay on. Now, based on the material and the color of the part, you should transfer the part to one of the slides. First, insert a buffer 0.2 step. Okay, so this is another step. We add it. Then insert alternative branches. Alternative branches here. You could add alternative branches. How you could add steps? By clicking on this one. Okay, so step and transition. This one is just a step, this one is just a transition. This one is end condition, and this one is jump. And here we have this alternative branching. Okay, so we have alternative branching, and now we have two transitions. To add the third branch, select the branch after buffer 0.2 step and click on the open alternative branch here. Now we need to add something inside these transitions. Add steps with transitions after each transition in the alternative branch. So add more, basically add one more branch. Add one more branch plus add steps with transitions. Okay. Use meaningful names for the steps. For the first one, metallic part, red part, and the black part. These are the names that we changed to. Update transitions 4 to 6 as below. So for the transition 4, if the part is metallic, then this sensor is true. If the part is not metallic, then in the next branch, we need to see if the part is not black. If the part is not metallic and not black, okay, then we should go to the third branch, and that branch should be true, okay, because at the time one of these conditions should be true, either the condition 4 or 5 or 6. Update the actions and transitions as below for metallic part now. Okay, so which one? This is the step 5. Okay, double click on the step 5 under actions. If the part is metallic, then the shunt 1 should be active, and the stopper also should be set to 1. What is the transition condition for the transition condition 7 or T7? Slide full. That means that the part is already slided into that slide, okay, or push into that slide, and we got the signal from the sensor. So once we got the signal from the sensor, then we could move forward. Update the actions and transitions as below for red part. Okay, so if the part is red, the shunt 2 should set to 1, and stopper also should set to 1. And what is the condition again? The slide full. Okay, that slide full is that the retroreflective optoelectric sensor. Okay, it means that the part is past that sensor or caught the laser beam of that sensor. And finally, update the action and transition as below for black part. Okay, for that one, we just need to set the stopper to 0. We don't need to move shunts. Okay, so when we say stopper to 0, it means that that stopper is retracted, that the stopper is releasing the part to move forward. Okay, why don't we need to set any shunt? Because this is the last slide, and if the part goes on the conveyor to the end, anyway, it will uh, it, basically it will fall into the last slide. Okay, and again for the transition, slide full sensor. Okay, now let's look at the program again. What do we have? We need to close the branches. Use the close branch command. This is the command. Okay, close the branches and add the last step with transition, call it finish. This is the last step. Okay, so you see the alternative branches. If the part is either metallic or red or black, and based on the sensor conditions in the transitions, we have proper actions inside each step and a transition. Okay, and now the last one, the finish. Let's see what do we have. Update the action and transition as below for the finish. So for the finish, we need to reset the stopper because the stopper should back to its place, and we need to reset the conveyor motor. We need to just stop the conveyor motor. Okay. Inside the transition, we don't have any condition. So we'll move immediately after setting or after executing these actions to the next step. Okay, the next one is just jumping. Insert the jump first by clicking on the double arrow. Okay, so there's a double arrow. Okay, click on that and then click on the jump instruction. This is the jump instruction. Choose step number 2 to jump into. Again, we could only jump into steps, and we want to jump into the step 2, which is the buffer one. Okay, now the program is ready to test. First test it in the simulation and then on the real setup. We don't have access to setup, but you could use the simulation. Call the instructor before downloading the project into the PLC, which is the real PLC. Since you're using the simulation, you could use the simulation without calling the instructor, of course. Okay. Now it is your turn to practice. Modify the graph code in order to apply the following. Take into account the push buttons and their associated LEDs on the control panel. The process could go to the initialization step and wait for the reset push button in order to reset the station. Then turn on flash the start button LED and wait for the start button to be pressed in order to process. Once the stop button is pressed, the system should finish one cycle and then go back to the initialization step and wait for the reset. Once one of the slides is full, the system should stop. Turn on flash one of the LEDs on the control panel and wait for the user to empty the slide and press reset in order to start over. Okay, so for the LEDs or other the coils, other the outputs, if you don't have the address of them, you could choose an arbitrary address. Okay, so choose an address by yourself. Why? Because anyway you are not going to use this program on a real device, but for example, for the real inputs, start with I. For real outputs, start with Q. If this is an internal contact or coil, start that with M. Okay. Test the program in a PLC sim and please upload it on Moodle.